Hey, welcome to the second video in IB Astrophysics. We're going to be looking today at the basics of how stars work. This is going to form the framework for most of the detail that comes later, so it's very important that you know this. And the first obvious fact about stars is that they're very bright. They're very far away, and yet we can still see them from Earth, which means that most of them emit enormous amounts of energy, and that energy comes from nuclear fusion. For 90% of stars, that fusion is hydrogen fusing into helium. The process is called the proton-proton chain. What you start out with are two normal hydrogen atoms, not deuterium and tritium, just regular hydrogen, and those run into each other at extremely high speeds and fuse into deuterium, or hydrogen 2. It's a neutron and a proton. Notice, though, that we had two protons to begin with, and now we have a proton and a neutron. So one of the protons had to turn into a neutron, and it does that by beta plus decay, and so you also get a neutrino and a positron out. And there's a lot of energy released, mainly in kinetic energy of the reagents, or of the products. And then that positron then usually goes and runs into an electron somewhere and produces even more energy through annihilation. Then what happens is, once you have that deuterium, it runs into yet another hydrogen atom, which is all over the place in a star. And this happens very, very quickly, and that forms helium-3. This process happens twice, because in the next step, you get two helium-3s, and that means each one of those has two protons and a neutron in it. Those collide with each other, and they turn into a helium-4, so we now have two protons, two neutrons, and also two more free protons. And then some energy in the form of gamma rays. It's typically two gamma ray photons. The net reaction is that you start out with four hydrogens turning into helium-4 plus two neutrinos and two positrons and some gamma rays and 26.7 mega electron volts of energy. That is a huge amount of energy for the mass involved, which is only really 4 protons. And that's where stars get all their energy from. You do not need to know the details of the proton-proton chain. What you do need to know is that hydrogen fuses into helium, and that's where stars get their energy. The rest is just interesting, but probably won't be asked about on the test. Another thing you need to know, though, are the conditions necessary for fusion. And this is very important, because fusion can only take place sometimes. You can't have fusion if it's cold, for instance. And you really need very high pressures and very high temperatures for fusion to happen. The reason you need high pressure or high temperatures is that the protons that initially react repel each other because they're both positively charged. Electrostatic force, two positive charges repel each other. And because they repel each other, but in order to react, they need to get very close. And the way you get things that are strongly repulsive to get really close is you have to shoot them at each other at extremely high speeds. And so for this reaction to occur, you need high kinetic energy. And well, we know that kinetic energy is related, average kinetic energy of a gas is related to its temperature. And you need very, very high temperatures for hydrogen fusion, much higher than the temperatures required in a thermonuclear weapon, which uses a different kind of fusion reaction. And typically, the core temperature of a star is on the order of 10 million kelvins, or on the order of millions of kelvins. And that's a main sequence star. Stars that use other fusion processes have even higher core temperatures. But we're talking about millions of kelvins here, which is a temperature that's so hot that you really have no sense for what that means. The outer layers of a star, though, are typically cooler. The part of the sun that we can see is typically on the order of thousands of kelvins rather than millions. So fusion only happens in the core, and that means the core is the part that needs the really high temperatures. Now, the fact is that stars are gas. They're not solids. So what holds them up against their own gravity? Gravity tends to make the whole thing contract because it's not a solid that you'd think that would just crush the star under its own weight. But there's lots of radiation produced in the core, mainly in the form of gamma ray photons. Those photons run into hydrogen atoms and other things, mainly hydrogen atoms, on their way out of the star. And what happens is that radiation exerts a pressure on the outer layers of the star, which counteracts the force of gravity. And in a stable star, what happens is that radiation pressure and gravity are roughly equal. And since stars that aren't stable typically explode and don't last very long, what we see are stars where gravity and radiation pressure balance each other. A consequence of this is that larger stars are more luminous, because a larger star has more gravity. And that means in order to stay stable, it needs to have more radiation pressure. And more radiation pressure means higher reaction rates, because it's producing more photons per second in order to balance out the higher gravity, and that means that it is more luminous. And typically the luminosity of the star varies as its mass raised to the 3.5, a power of approximately 3.5, which means if you double the size of a star, you're going to increase its luminosity by nearly a factor of 10. Another consequence of this is that because the large stars are more luminous and they burn fuel faster, they typically have shorter lifetimes. Meaning on the order of millions of years as opposed to the sun, which will have a lifetime of approximately 10 billion years. So what you need to know about stars, you need to know that they fuse hydrogen into helium to get their energy. You need to know that for that to happen, you need very high temperatures, and explain why. And you need to explain why a star is stable in terms of the radiation pressure and gravity, and why large stars are more luminous and shorter lived than small stars.